Beneath the tranquil beauty of our world, the rolling hills, the serene lakes, the vast national parks, lies a power of unimaginable scale. It is a force that does not answer to seasons, borders, or civilizations. For most of human history, its true nature was a mystery, a sleeping giant hidden deep within the Earth's crust. But when these giants stir, they do not just shake the ground, they rewrite the planet. They unleash an energy equivalent to thousands of atomic bombs, launching continents of ash into the stratosphere. This ash can veil the sun, not for a day or a week, but for years, even decades, plunging the world into a prolonged twilight. These are the supervolcanoes, the architects of ancient extinctions, and the silent threat that still pulses beneath our feet. Their story is not just one of geology, it is the story of survival against the odds, a forgotten chapter in the history of life itself. Beneath some of the most serene and beautiful landscapes on Earth, an incomprehensible power lies dormant. In the heart of North America, Yellowstone National Park attracts millions with its vibrant hot springs and explosive geysers. These geothermal wonders are celebrated as miracles of nature, but they are merely the surface-level symptoms of a colossal heat engine churning deep within the planet's crust. This is not a typical volcano, a familiar cone-shaped mountain reaching for the sky. This is something else entirely, a force of a different order of magnitude. This is a supervolcano. The term itself evokes images of immense destruction, but the reality of these geological structures is far more subtle and sprawling. Supervolcanoes often have no mountain at all. Instead, they are identified by enormous depressions in the ground, known as calderas. The Yellowstone caldera, for example, is a vast basin measuring roughly 70 by 45 kilometers, so large that its full extent can only be appreciated from space. It is the scar left behind by an eruption of almost unimaginable violence. Beneath this tranquil park lies a magma chamber of staggering proportions, a massive reservoir of molten and semi-molten rock stretching for many kilometers underground. The heat radiating from this chamber powers every geyser and warms every thermal pool. It is the lifeblood of the park's unique ecosystem, but it is also a reminder of the potential for a cataclysmic awakening. Yellowstone is not alone. Across the globe, other giants slumber. In Italy, near the bustling city of Naples, lies the Campi Flegrei, or Phlegrean fields, a sprawling caldera where the ground regularly breathes, rising and falling with the pressure of the magma below. In New Zealand, the idyllic Lake Taupō fills the caldera of a supervolcano responsible for one of the most violent eruptions of the last 25,000 years. These sites, and others like them, are windows into the deep, fiery heart of our planet. They are monitored constantly by scientists who understand that the calm is deceptive. The pressure is always building, the rock is always shifting, and the heat is relentless. The forces that created these calderas have not vanished. They have merely entered a period of repose. We walk upon the thin crust of a restless world, often unaware of the immense energies contained just beneath our feet. These sleeping giants are a fundamental part of our planet's geological cycle, a system of creation and renewal that operates on a timescale far beyond human comprehension. But what happens when one of them stirs? What truly defines an eruption so powerful that it earns the prefix super? In 1980, the world watched as Mount St. Helens in Washington state erupted with formidable force. It was a stark demonstration of nature's power, an event that reshaped a mountain and altered the surrounding landscape for decades. Yet, in the grand theater of planetary geology, this powerful blast was a minor act. To understand the true scale of a super-eruption, we must first have a way to measure it. Scientists use the Volcanic Explosivity Index, or VEI, a scale from 0 to 8, that classifies eruptions based on the volume of material ejected. Much like the Richter scale for earthquakes, the VEI is logarithmic. Each whole number represents an eruption 10 times more powerful than the one before it. The eruption of Mount St. Helens registered as a VEI 5. The colossal 1883 eruption of Krakatoa in Indonesia, which was heard thousands of kilometers away, was a VEI 6. The 1991 eruption of Mount Pinatubo in the Philippines, which ejected so much material into the atmosphere that it temporarily cooled the entire planet, was also a VEI 6. These were historic, globally significant events. But the scale does not end there. A VEI 7 is 10 times larger still. And then there is the top of the scale, VEI 8. This is the domain of the supervolcano. A VEI 8 eruption is defined as one that ejects a minimum of 1,000 cubic kilometers of rock, ash, and magma. It is a volume that defies easy comparison. It is enough material to bury a large country under a thick blanket of debris. It is more than 250 times the amount ejected by Krakatoa. An event of this magnitude does not simply blow the top off a mountain. Instead, the sheer volume of magma evacuating the chamber below causes the overlying crust to collapse. The ground itself gives way, plunging downwards to form a massive caldera. This is not an explosion in the conventional sense. It is a fundamental reordering of the Earth's surface over an enormous area. The immediate aftermath is a scene of utter transformation as pyroclastic flows, superheated avalanches of gas and ash, travel at immense speeds, incinerating everything in their path for hundreds of square kilometers. But the true impact of a VEI 8 event is not local. It is global. The sheer quantity of ash and sulfur gases injected into the stratosphere is enough to fundamentally alter the planet's climate for years, even decades. With this scientific framework, we can begin to comprehend the forces at play. We have a definition for the unthinkable. The next question is a chilling one. Where is the evidence that such an event has ever happened in our planet's history? The evidence of ancient super-eruptions is not found in historical texts or human memory. It is written in the very rock beneath our feet and preserved in the most remote corners of the globe. For geologists, hunting for the fingerprints of these cataclysms is a form of planetary detective work. The most crucial clue is a substance known as tephra, the layer of rock fragments and ash from a volcanic eruption. When a supervolcano erupts, it launches this material high into the stratosphere, where winds can carry it across entire continents and oceans. As this fine ash eventually settles, it forms a distinct layer in the geological record. Finding such a layer, sometimes thousands of kilometers from its source, is the geological equivalent of discovering a crime scene. By analyzing the unique chemical signature of the ash, scientists can trace it back to its parent volcano. This process has allowed them to map the reach of eruptions that occurred millions of years ago. In North America, vast deposits known as the Huckleberry Ridge Tuff are the calling card of Yellowstone's colossal eruption 2.1 million years ago. This single event deposited a layer of ash across much of the continent, a silent testament to its incredible power. Similarly, the Orowanui eruption of New Zealand's Taupō volcano, around 26,500 years ago, left its chemical fingerprint across thousands of square kilometers of the southern Pacific. But perhaps the most precise records of these ancient events are found frozen in time. In the immense ice sheets of Greenland and Antarctica, each year's snowfall compresses into a new layer of ice, creating a perfect, year-by-year archive of the Earth's climate stretching back hundreds of thousands of years. When a massive volcanic eruption occurs anywhere on the planet, its fine ash and sulfur aerosols are carried by atmospheric circulation to the poles, where they fall and are trapped in the ice. Scientists can drill deep into these ice sheets, extracting cores that reveal these ancient events as distinct, dark bands. By analyzing the particles and the chemistry of the surrounding ice, they can not only identify the eruption, but also precisely date it and measure its impact on the atmosphere. These frozen chronicles tell a dramatic story. They show that VEI-8 eruptions are a recurring, if infrequent, feature of our planet's history. They are not theoretical possibilities, but confirmed realities. And as the geological and ice core records become clearer, one event in particular stands out. It occurred in the relatively recent past, an eruption so powerful that it may have directly intersected with the story of our own species, pushing our early ancestors to the very brink of existence. In the heart of Sumatra, Indonesia, lies Lake Toba. It is the largest volcanic lake on Earth, a place of stunning natural beauty and serene tranquility. But this peaceful landscape hides a violent past. The lake fills the immense caldera left behind by one of the most powerful volcanic eruptions of the last 2 million years. Approximately 74,000 years ago, the Taupō supervolcano awakened in an explosion that fundamentally altered the course of life on this planet. The Taupō eruption was a monster, a confirmed VEI-8 event on the Volcanic Explosivity Index. It unleashed nearly 3,000 cubic kilometers of magma and rock, an amount that dwarfs any eruption in recorded human history. The immediate consequences were apocalyptic for the region. Pyroclastic flows, superheated currents of gas and ash, would have swept across an area of at least 20,000 square kilometers, transforming the landscape into a sterile, ash-covered wasteland. But the true, lasting impact of Taupō was not regional. It was global. The eruption injected a colossal amount of sulfur dioxide into the stratosphere. Once there, these gases reacted with water to form a dense veil of sulfate aerosols that shrouded the entire planet. This veil acted like a planetary sunshade, reflecting incoming sunlight back into space and causing a dramatic drop in global temperatures. This phenomenon is known as a volcanic winter. Evidence from Greenland ice cores suggests that following the Taupō eruption, the Earth experienced a sudden and severe cooling period that may have lasted for years, possibly even a decade, followed by a 1,000-year-long cold spell. For the small populations of early modern humans living at the time, this would have been a catastrophe. This has led to the Taupō catastrophe theory, a compelling but debated hypothesis that suggests the eruption created a dramatic population bottleneck. According to this theory, the harsh, sunless years that followed Taupō's eruption caused a collapse in ecosystems worldwide. Plants withered, and the animals that humans relied upon for food disappeared. The theory posits that the global human population was reduced to a mere few thousand individuals, a small group of survivors who endured this prolonged period of hardship. While the exact numbers are still a subject of scientific debate, genetic evidence does point to a time in our deep past when human genetic diversity was remarkably low, consistent with a population that had passed through a severe bottleneck. The world after Taupō was a different place. It was a colder, harsher planet where survival was a daily struggle. For our ancestors, it was a test of resilience and adaptability unlike any other. They were a young species, facing a planetary challenge that threatened their very existence. The eruption of a supervolcano is not a singular event, but the beginning of a long and arduous planetary transformation. The aftermath of an event like Taupō plunged the world into a prolonged twilight, a state often referred to as a volcanic winter. The mechanism is brutally efficient. The vast cloud of sulfate aerosols in the stratosphere blocks a significant percentage of incoming sunlight, starving the Earth's surface of the light and warmth it needs to sustain life. Global average temperatures would have plummeted by several degrees Celsius within a year, triggering an abrupt and severe climate shift. This rapid cooling would have been devastating for ecosystems that were adapted to a stable climate. In the tropics, the sudden cold would have been a shock, while in temperate zones, growing seasons would have failed completely. For years, the sky would have been a hazy, unfamiliar gray, with the sun appearing as a pale, distant disk. The chemical fallout would have been just as severe. The same sulfur compounds that blocked the sun would have combined with atmospheric moisture to create widespread acid rain, poisoning freshwater sources and damaging foliage on a global scale. The physical blanket of ash itself presented another challenge. While meters thick near the eruption site, a layer of several centimeters could have covered entire continents. This fine, abrasive dust would have smothered plant life, contaminated water supplies, and posed a significant hazard to any air-breathing creature. For the small bands of early humans and other species that survived the initial event, the world became profoundly hostile. It was a desperate struggle for resources on a planet where the fundamental rules of nature had been rewritten. The once reliable patterns of seasons, animal migrations, and plant growth were thrown into chaos. Survival would have depended on ingenuity, cooperation, and the ability to adapt to a much colder, darker world. Yet, life is resilient. And humanity, even in its early stages, proved to be remarkably so. This period of extreme environmental stress may have acted as a powerful evolutionary driver, favoring groups that were more innovative and socially cohesive. It may have spurred new hunting techniques, better methods of food storage, and forced migrations to coastal areas or geothermal hotspots where life was more tenable. Reflecting on this deep past forces us to consider our present vulnerability. Our modern global civilization, with its intricate supply chains and reliance on agriculture, is in many ways more fragile than the hunter-gatherer societies of the past. A Taupō-scale eruption today would not just be a natural disaster, it would be a challenge to the very foundations of our interconnected world. The sleeping giants are not extinct. They are a permanent feature of our planet's geology. The question is not if another super-eruption will occur, but when and how we will face a world where the sun itself seems to turn away. Sometime around 74,000 years ago, our species faced a moment of near extinction. An event so profound, it left an indelible mark on the genetic code of every human alive today. This is the story of the Great Human Bottleneck, a period when the population of our ancestors plummeted to perhaps only a few thousand individuals. For decades, scientists puzzled over the cause. What could have brought humanity to the very edge of annihilation? The answer, many believe, was written in ash and sulfur, blasted from the heart of a colossal volcano. The Taupō super-eruption in Sumatra, Indonesia, was an event of unimaginable scale. It ejected nearly 3,000 cubic kilometers of rock and ash into the atmosphere, an amount that would bury the entire state of California under several feet of material. This wasn't just a regional disaster, it was a planetary crisis. The immense plume of aerosols and fine ash encircled the globe, reflecting sunlight back into space. The effect was a volcanic winter that may have lasted for a decade, followed by a cooling period that endured for 1,000 years. Temperatures dropped dramatically. Ecosystems collapsed. In this new, harsh world, the rules of survival changed overnight. Early human populations, scattered across Africa, Asia, and Europe, faced relentless challenges. Food sources that had sustained them for generations vanished. The cold was persistent, and the sky, veiled by a persistent haze, offered little warmth. It was a filter, a great test of resilience and adaptability. Genetic studies reveal that modern humans outside of Africa show remarkably little genetic diversity, a telltale sign of a population that has recovered from a very small number of ancestors. We are the descendants of the survivors. These were small bands of resourceful, intelligent hominins who found ways to endure the long winter. They adapted their hunting techniques, found new shelters, and strengthened their social bonds to overcome the immense environmental pressures. They were not just lucky, they were pioneers of perseverance. The story of the Taupō bottleneck is a humbling reminder of nature's power and our own fragility. It raises a chilling question. If a single eruption could push our species to the brink once, what would a similar event mean for our complex, interconnected world today? The planet's deep heat remains, and other giants lie sleeping. In the heart of North America lies a landscape of breathtaking beauty, a celebrated wilderness that attracts millions of visitors each year. Yellowstone National Park. It is a place of vibrant colors, where geothermal wonders paint the ground in hues of orange, yellow, and turquoise. Geysers, like the famed Old Faithful, erupt with clockwork precision, sending columns of steam and hot water high into the sky. Bison roam vast grasslands, and pristine rivers cut through majestic canyons. This is the Yellowstone the world knows and loves, a sanctuary of natural splendor, a testament to conservation. But this serene beauty conceals a secret of immense and terrifying power. The entire park, with its geysers, hot springs, and bubbling mud pots, is merely the surface expression of a geological giant. Beneath the picturesque landscape lies one of the largest active volcanic systems on Earth. Yellowstone is not just a volcano, it is a supervolcano. The park itself sits within a massive caldera, a collapsed crater over 70 kilometers across, formed by an ancient eruption of almost incomprehensible force. The heat that powers Old Faithful and the Grand Prismatic Spring emanates from a colossal magma chamber lurking just a few kilometers below the surface. This chamber is a vast reservoir of partially molten rock, a sleeping beast whose slow, rhythmic breathing causes the ground itself to rise and fall by centimeters each year. Scientists at the Yellowstone Volcano Observatory monitor this giant's every stir. They use a sophisticated network of seismometers, GPS stations, and satellite imagery to track ground deformation, earthquake swarms, and changes in geothermal activity. They are the sentinels, watching for any sign that the beast is beginning to awaken. The park's beauty and its underlying power are two sides of the same coin. The very forces that could one day unleash a cataclysmic eruption are the same ones that create the stunning geothermal features visitors travel the world to see. It is a profound paradox, a place of tranquility and life that rests upon a source of planetary-scale destructive potential. Understanding this duality is key to comprehending the true nature of Yellowstone. It is both a paradise and a ticking geological clock, a constant reminder that the Earth's most beautiful places can also be its most formidable. The question is not if it will erupt again, but when, and what clues from its violent past can tell us about our future. 2.1 million years ago, the land that would one day become Yellowstone was the epicenter of one of the most violent volcanic events in Earth's history. This was not an eruption. It was a planetary reconfiguration. Known to geologists as the Huckleberry Ridge Tuff eruption, it was the first and largest of Yellowstone's 3 super-eruptions. The sheer scale of this event dwarfs any volcanic activity witnessed in modern times. It released 2,500 times more ash than the 1980 eruption of Mount St. Helens. The eruption began with a titanic explosion that tore a hole in the Earth's crust. A column of ash and superheated gas rocketed more than 30 kilometers into the stratosphere, punching through the atmosphere with unimaginable energy. This colossal plume spread outwards, forming a vast umbrella cloud that began to block out the sun across the continent. But the most destructive force was yet to come. As the eruption column became too dense to support its own weight, it collapsed. This triggered pyroclastic flows, fast-moving, ground-hugging avalanches of hot gas, ash, and rock fragments, reaching temperatures of hundreds of degrees Celsius. They moved at hurricane speeds, incinerating everything in their path. These flows covered over 15,000 square kilometers, an area larger than the state of Connecticut, burying the landscape under hundreds of meters of hot volcanic debris, which welded together to form a rock layer known as the Huckleberry Ridge Tuff. The immediate area was sterilized, but the global consequences were just beginning. Ash from this single eruption has been found as far away as California, Missouri, and even the Gulf of Mexico. It blanketed much of North America, creating a volcanic winter that altered the climate for years. Ecosystems were disrupted, and the course of evolution for many species was undoubtedly changed. The eruption was so massive that the ground above the emptying magma chamber collapsed, forming the first of Yellowstone's giant calderas. The event literally reshaped the continent. Studying the Huckleberry Ridge Tuff today gives scientists a window into the raw power of a supervolcano. By analyzing the chemistry and distribution of these ancient ash beds, they can reconstruct the eruption's dynamics and better understand the mechanisms that drive these rare but catastrophic events. It is a geological ghost story, a tale of a day when the ground opened, and a force from deep within the earth remade the world. How do you see something that is buried 8 kilometers beneath the surface of the earth? How do you map the anatomy of a sleeping giant? For the scientists at the Yellowstone Volcano Observatory, this is the fundamental challenge. They are tasked with understanding the intricate plumbing system of the Yellowstone supervolcano, a complex network of molten and semi-molten rock that fuels the park's famous geothermal activity. The key is to use technology to peer deep into the crust. One of the most powerful tools is seismic tomography. It works much like a medical CAT scan, but instead of X-rays, it uses seismic waves from earthquakes. Yellowstone experiences thousands of small earthquakes each year. When these tremors occur, seismic waves travel through the ground. By measuring the speed of these waves at hundreds of monitoring stations, scientists can create a three-dimensional image of what lies beneath. The waves travel slower through hot, partially molten rock than they do through solid, cold rock. This allows geophysicists to identify the location, size, and shape of the magma reservoirs. The results of these studies are astonishing. They have revealed not one, but 2 massive magma chambers stacked on top of each other. The upper chamber, smaller and filled with a sticky, gas-rich rhyolitic magma, sits about 5 to 17 kilometers deep. Below, it lies a much larger reservoir of hotter, more fluid basaltic magma, extending down to nearly 50 kilometers. This lower chamber is more than 4 times the size of the upper one. But seismic imaging is just one piece of the puzzle. Scientists also rely on GPS measurements of incredible precision. A network of stations across the caldera can detect minute changes in the ground's elevation. The entire caldera floor slowly rises and falls as magma and geothermal fluids shift deep below, a process that has been described as the volcano breathing. INSAR, or Interferometric Synthetic Aperture Radar, uses satellites to create detailed maps of this ground deformation over vast areas, providing a broader context for the GPS data. By combining these different streams of information, seismicity, ground movement, gas emissions, and geothermal heat flow, a coherent picture of the beast begins to emerge. We can now visualize the vastness of the system hidden beneath the beauty of the park. This continuous monitoring is our best defense, providing the crucial early warnings needed if the system ever begins to show signs of reawakening. While Yellowstone commands global attention, another supervolcano on the opposite side of the planet is responsible for the most recent super-eruption on Earth. Located on New Zealand's North Island, the Taupō volcanic zone is one of the most active geothermal areas in the world. And around 26,500 years ago, it produced the Orowanui eruption, an event that profoundly reshaped the nation's geography and had a significant global impact. The Orowanui eruption was the largest known eruption in the world in the last 70,000 years. While it ejected less total material than Yellowstone's Huckleberry Ridge event, its power and intensity were staggering. It discharged over 1,100 cubic kilometers of volcanic material, with more than half of that being unleashed in a matter of minutes. Its most devastating feature was an enormous, fast-moving pyroclastic flow. This scorching current of gas and rock traveled at hundreds of kilometers per hour, overwhelming the landscape. It was so vast, it buried the entire central North Island, an area of 20,000 square kilometers, under a thick blanket of ignimbrite. The rock formed from this flow. It filled valleys, dammed rivers, and created a new, flattened plateau. The eruption column reached 50 kilometers high, deep into the stratosphere. Fine ash was carried by atmospheric currents across the globe. Layers of Orowanui ash have been identified in ice cores from Antarctica, over 5,000 kilometers away, providing a precise date for the event and a clear marker of its global reach. When the fury subsided, the ground above the emptied magma chamber collapsed, creating a massive caldera. This depression slowly filled with water, forming what is today New Zealand's largest lake, Lake Taupō. The beautiful, serene lake that is now a hub for recreation and tourism is, in fact, the water-filled crater of a planetary-scale cataclysm. The eruption had a lasting impact on the climate, contributing to a period of global cooling. For the local ecosystem, it was a complete reset. The landscape was sterilized, and it would take centuries for life to reclaim the ash-covered terrain. The Orowanui eruption serves as a powerful reminder that the forces that drive supervolcanoes are a global phenomenon. It demonstrates that even in geologically recent times, the planet is capable of producing events that can alter continents and influence the climate of the entire world, leaving behind legacies of both destruction and stunning natural beauty. In the shadow of Mount Vesuvius, along the sun-drenched coast of Italy, lies a danger far greater than the peak that buried Pompeii. It is not a mountain, but a sprawling, sunken landscape of craters, steam vents, and hot springs. This is Campi Flegrei, the Phlegreian Fields. To the unsuspecting eye, it is a beautiful, geothermally active region. To geologists, it is one of the most dangerous supervolcanoes on Earth, a hidden threat simmering beneath 3 million people. Unlike the iconic cone of Vesuvius, Campi Flegrei is a massive caldera, the collapsed remnant of colossal past eruptions. Its history is written in the very stone used to build the city of Naples. Around 39,000 years ago, the caldera unleashed the Campanian ignimbrite eruption, a cataclysmic event that ejected over 200 cubic kilometers of magma. The eruption was so immense that its ash has been found as far away as the Russian plains. It triggered a volcanic winter across Europe, altering the climate for years and potentially contributing to the pressures faced by Neanderthal populations. It was one of the largest eruptions on the continent in the last 200,000 years. But the giant was not finished. A second major event, the Neapolitan Yellow Tuff eruption, occurred around 15,000 years ago, further shaping the landscape and blanketing the region. Since then, the volcano has remained active, with dozens of smaller eruptions, the most recent in 1538, which created a new cinder cone, Monte Nuovo, in just a week. The most unsettling feature of Campi Flegrei is a phenomenon known as bradyseism. The ground itself breathes, rising and falling as the magma chamber beneath fills and shifts. The ancient Roman marketplace in the town of Pozzuoli stands as a silent witness. Its stone pillars are pockmarked by marine mollusks, clear evidence that the entire structure was once submerged by the sea before being lifted up again by the restless earth. In recent decades, this breathing has become more pronounced. Periods of rapid uplift in the 1970s and 1980s forced temporary evacuations. Today, the ground is rising once more. Seismicity is increasing, and gas emissions are changing. The scientific community watches with intense focus, monitoring every tremor, every subtle change. The people of Naples and Pozzuoli live their lives atop a geological time bomb. They are accustomed to the tremors and the steam, but the knowledge of the power beneath them is an ever-present reality. The question is not if it will erupt again, but when, and with what force. As pressure builds deep within the Earth, we are forced to confront the anatomy of such an event. What truly happens when a supervolcano awakens? What defines a super-eruption? It is an event of almost incomprehensible scale, an outburst of planetary force that begins deep within the Earth's crust. The process starts with the slow accumulation of magma in a colossal subterranean chamber, a reservoir of molten rock that can be many kilometers wide. Over tens of thousands, or even hundreds of thousands of years, this chamber grows. It is fed by hotter, more primitive magma from the mantle below. This new material heats the existing silica-rich magma, making it less dense and increasing the concentration of trapped gases like water vapor and carbon dioxide. The chamber swells, pushing the ground above it upwards by meters, a subtle but ominous sign of the immense pressure building below. The trigger for the eruption is the point of no return. It could be a new, massive injection of magma from below, overpressurizing the system like a shaken bottle of soda. It could be a large earthquake, fracturing the rock that contains the chamber and creating a path of weakness. Or the chamber could simply grow so large that the roof of rock above it can no longer support its own weight. Whatever the cause, the result is the same: a catastrophic failure of the chamber's roof. With the pressure suddenly released, the dissolved gases in the magma expand violently, creating a foam of molten rock and gas that blasts towards the surface. The eruption itself unfolds in stages of escalating intensity. First, a colossal column of ash, gas, and pulverized rock is ejected into the atmosphere at supersonic speeds. This is a Plinian column, but magnified 1,000 times. It can reach heights of over 40 kilometers, punching through the troposphere and into the stratosphere. From this height, winds can carry the fine ash around the globe, but the column cannot sustain its own immense weight forever. As it loses upward momentum, it collapses back upon itself. This is when the most destructive phase begins: the pyroclastic flows. These are not lava flows. They are superheated, turbulent avalanches of ash, pumice, and gas, moving across the landscape at hundreds of kilometers per hour. They are a force of nature that can incinerate and bury everything in their path over thousands of square kilometers. The eruption may last for days or weeks, a continuous outpouring of energy that fundamentally alters the world. And when the fury subsides, the land itself is forever changed, leaving behind a monumental scar. After the fire, the ash, and the roar, a profound silence descends. The mountain that once dominated the horizon is gone. The land where it stood has vanished. In its place is a vast circular depression, a great bowl carved into the planet. This is the caldera, the enduring signature of a super-eruption. It is not a crater blasted out by an explosion, but a feature of immense subsidence. The eruption has emptied the massive magma chamber below, leaving a void. The overlying crust, now without support, collapses into the empty space, creating a geological basin that can be dozens of kilometers across. These scars are scattered across the globe, often hidden in plain sight, as features of remarkable beauty. Crater Lake in Oregon is one of the world's most pristine lakes, filling the caldera of Mount Mazama, which erupted nearly 8,000 years ago. Lake Taupō, the largest lake in New Zealand, occupies the caldera of a supervolcano that produced one of the largest eruptions in the last 70,000 years. And in Indonesia, the serene Lake Toba fills the 100-kilometer-long caldera left by the Toba super-eruption, an event so massive it may have impacted human evolution. Perhaps the most famous active example is the Yellowstone caldera in North America. Its sheer size, roughly 55 by 72 kilometers, meant it was not even recognized as a single volcanic feature until it was viewed from space. Today, the park's famous geothermal wonders, the geysers, hot springs, and fumaroles, are all expressions of the immense heat engine that still churns just a few kilometers beneath the surface. They are beautiful reminders that the system is not extinct, but merely dormant. Calderas are not static monuments to the past. They are living, breathing systems. After a major eruption, magma can begin to accumulate once more in the chamber below. As it does, it can push the floor of the caldera upwards, creating what geologists call a resurgent dome. In Yellowstone, both the Sour Creek Dome and the Mallard Lake Dome have been rising and falling for thousands of years, evidence of the magma's restless movement. This cycle of collapse and resurgence demonstrates that a caldera is not an end, but part of a long, slow volcanic life cycle. These vast scars are windows into the deep earth, and by studying them, we can read the story of the planet's most powerful events and find clues to what might happen in the future. For most of human history, a volcanic eruption was an unpredictable act of nature, a sudden and terrifying display of power. Today, we have moved from mythology to monitoring. In observatories around the world, scientists are learning to interpret the subtle language of an awakening volcano, searching for the warning signs of a future eruption. Predicting the behavior of a supervolcano is one of the greatest challenges in modern geology, a high-stakes effort to provide warning before a global catastrophe. The most fundamental tool is seismic monitoring. A dense network of seismometers is placed around a caldera system like Yellowstone or Campi Flegrei. These sensitive instruments listen constantly for the faintest tremors in the earth. Scientists learn to distinguish the signature of normal tectonic earthquakes from the unique seismic signals generated by magma, moving, rock fracturing, and fluids resonating deep underground. A swarm of small, shallow earthquakes can be a key indicator that magma is on the move, pushing its way towards the surface. Another critical sign is ground deformation. The land itself swells and subsides as the magma chamber beneath it inflates and deflates. Modern technology provides an unprecedented view of this movement. Networks of high-precision GPS stations can detect changes in elevation as small as a few millimeters. A more powerful tool is INSAR, or Interferometric Synthetic Aperture Radar. By comparing satellite radar images taken at different times, scientists can create detailed maps of ground movement over vast areas, revealing the subtle breathing of the giant below. Volcanoes also exhale. As magma rises, the decreasing pressure allows dissolved gases to escape. Scientists at volcanic observatories regularly sample gases released from fumaroles and vents, looking for changes in their chemical composition. A sudden spike in the output of sulfur dioxide, for example, is a classic sign that fresh magma is nearing the surface. Changes in the temperature of hot springs, or the water chemistry of lakes and rivers, can also provide clues about what is happening in the subterranean plumbing. There is no single silver bullet for prediction. Instead, scientists look for a combination of these signals: increased seismicity, rapid ground uplift, and changing gas emissions, all occurring together. The goal is not to predict the exact day and hour, but to recognize a pattern of escalating unrest that allows authorities to make informed decisions, to raise alert levels, and, if necessary, to issue an evacuation. It's a race against time, using science to decipher the planet's most powerful secrets. Imagine the headlines. After weeks of escalating earthquake swarms and rapid ground deformation, the Yellowstone Volcano Observatory raises the alert level to its highest point. A mandatory evacuation is ordered for a radius of hundreds of kilometers. The world watches, holding its breath. Then, it happens. The eruption begins, not as a single explosion, but as a series of vents tearing open across the caldera floor, unleashing a fury that dwarfs any volcanic event in recorded history. In the first hours and days, the immediate region would be devastated. Pyroclastic flows, moving at the speed of a jetliner, would obliterate everything within a 100-kilometer radius, an area larger than many small countries. The sky would turn to night as the eruption column climbs 40 kilometers into the stratosphere. Then comes the ash. Within a day, a thick blanket of heavy gray powder would cover states like Wyoming, Montana, and Idaho, collapsing buildings under its weight and shutting down all forms of transportation. The ash, made of tiny, sharp particles of rock and glass, would be a severe respiratory hazard and would contaminate water supplies across the western United States. As the ash cloud spreads across North America and then around the globe, the cascading consequences would begin. Air travel worldwide would be grounded indefinitely. The fine ash particles can damage and destroy jet engines, making flight impossible. The modern global economy, built on just-in-time supply chains, would grind to a halt. Communication systems, power grids, and water treatment facilities would fail. Agriculture would face an unprecedented crisis. Crops across entire continents would be buried or fail to grow due to the lack of sunlight. The immediate impact on the world's food supply would be catastrophic. The longest-term effect would be on the climate. The vast quantity of sulfur dioxide injected into the stratosphere would form a haze of sulfate aerosols, reflecting sunlight back into space. Global average temperatures could drop by several degrees, triggering a volcanic winter that could last for a decade or more. Growing seasons would shorten or vanish, leading to widespread famine and societal instability. Our interconnected, technologically dependent civilization has never faced a challenge of this magnitude. A super-eruption is not just a geological event, it is a civilization-altering one. It is a stark reminder that we are guests on a powerful and dynamic planet whose deep geological clock is still ticking. The first sign was not a sound, but a sight. Across the globe, sunsets began to blaze with an unearthly, spectacular intensity. Hues of fiery orange and deep violet painted the evening sky, a beautiful and ominous spectacle that artists like J.M.W. Turner would famously capture on canvas. But this was no ordinary atmospheric event. It was the calling card of a catastrophe, the fine veil of sulfate aerosols cast into the stratosphere by a colossal volcanic eruption thousands of miles away. Soon, the beauty gave way to a persistent, chilling dimness. The sun, once a brilliant source of life and warmth, became a pale, muted disk in the sky, often visible to the naked eye without discomfort. This strange, dry fog, a sulfuric acid haze, was a global shroud that reflected solar radiation back into space. The consequences were swift and severe. Global temperatures plummeted by several degrees, initiating a period of profound climate disruption. The most famous and well-documented of these events followed the 1815 eruption of Mount Tambora, leading to what became known in the Northern Hemisphere as 1816, the year without a summer. In New England, snow fell in June. Frosts in July and August withered burgeoning crops in the fields. Across Europe, the weather turned chaotic and relentlessly cold. Persistent, heavy rains caused major rivers to flood, turning farmland into swamps. The grape harvests in France failed completely, and the grain harvests across the continent were disastrously poor. The disruption to the seasons was profound and disorienting. People who lived by the predictable rhythm of planting and harvesting found their world turned upside down. They lit fires in midsummer, not for comfort, but for survival against the unseasonable chill. The natural world was in disarray. Birds fell from the sky, and livestock, deprived of fodder, perished. This wasn't just a bad weather year. It was a fundamental break in the planet's engine, a chilling demonstration of how a single geological event could hijack the world's climate. In the eerie twilight of that Swiss summer, a group of English writers, trapped indoors by the incessant rain, passed the time by telling ghost stories. It was there that a young Mary Shelley conceived the tale of Frankenstein, a story born from a world that seemed to have been abandoned by the sun. The atmospheric gloom had seeped into the human imagination, but the real-world consequences were far more immediate. The failed harvests were not an abstract problem. They were the prelude to a much deeper crisis. The strange, cold twilight was just the beginning. The real challenge was not the lack of warmth, but the impending lack of food. For a plant, sunlight is life. When the sun vanishes behind a persistent volcanic haze, the fields fall silent. The climatic chaos of the year without a summer was not just an inconvenience, it was a direct assault on the very foundation of human civilization, agriculture. Across the northern hemisphere, the chain reaction of crop failure began. In North America, corn, a staple crop, failed to mature in the short, cold growing season. In Ireland, the constant cold and rain decimated the potato crop, a grim foreshadowing of the greater famine that would strike decades later. In Switzerland, the situation grew so dire that people were reportedly eating moss and cats to survive. The price of grain, the basic currency of life for most of the population, skyrocketed. In some parts of Europe, oat prices increased eightfold. This wasn't just inflation, it was the transformation of bread from a daily staple into an unattainable luxury. Governments, unprepared for a crisis of this scale, were slow to react. Their granaries were quickly depleted, and the infrastructure for mass food distribution was inadequate. Hoarding became rampant among those with the means, while desperation drove the poor to protest. Food riots erupted in towns and cities across Britain, France, and Germany. Bakeries were looted, and grain convoys were attacked by hungry mobs. The crisis was not confined to Europe and North America. The volcanic aerosols also drastically disrupted the Asian monsoon cycle. In India, the summer monsoon failed, leading to a severe drought. This, in turn, triggered a new, virulent strain of cholera in the Ganges Delta, an epidemic that would eventually spread across the globe over the next decade, a long-tail consequence of the eruption. In the Yunnan province of China, the 3-year-long cold and disruption to rice cultivation led to a widespread and devastating famine. People were forced to abandon their ancestral lands, becoming refugees in their own country, searching for any region untouched by the blight. This mass migration put immense pressure on neighboring communities, creating social friction and conflict. The global famine was a stark reminder of the fragility of the human food supply. In an age before mechanized agriculture and global shipping networks, communities were almost entirely dependent on their local harvest. When that harvest failed, not just in one region but across an entire hemisphere, the results were catastrophic. As hunger gnawed at the foundations of communities, a new, more profound question arose. How does a civilization hold itself together when its people are starving? Hunger is the parent of revolution. When the granaries are empty, the thrones of kings begin to tremble. The crisis triggered by the volcanic winter was more than an agricultural disaster. It became a catalyst for profound social and political upheaval. The bonds that held society together began to fray under the relentless pressure of starvation and uncertainty. As governments failed to provide relief, their authority and legitimacy crumbled. The food riots were merely the first tremor. They were followed by a surge in crime and lawlessness as desperation drove ordinary people to extraordinary measures. In the countryside, bands of displaced and hungry people roamed, creating an atmosphere of fear and instability. The social order, once taken for granted, seemed on the verge of collapse. The crisis also fueled mass migrations. The Great Migration westward in the United States accelerated dramatically in the years following 1816 as families abandoned their failed farms in New England in search of more fertile land in the Ohio River Valley. This massive internal displacement reshaped the demographic map of the young nation. In Europe, the widespread suffering contributed to a febrile political atmosphere, fostering the social unrest and revolutionary ideas that would simmer throughout the 19th century. Beyond the immediate social chaos, a more insidious threat emerged: disease. Malnourished populations are uniquely vulnerable to infection. The cholera epidemic that began in Bengal was a direct consequence of the drought, but its rapid spread was facilitated by a world of weakened immune systems. Typhus epidemics also flared up across Europe, spreading rapidly in the impoverished and overcrowded urban centers where many had fled in search of aid. This perfect storm of famine, disease, and social breakdown pushed many communities to the brink. It was a test of resilience on a scale rarely seen. Some societies fractured, while others adapted. New farming techniques were explored, and new crops, like the hardier potato, became more widely adopted in parts of Europe as a hedge against the failure of grain. But the lesson was a harsh one. A single event, originating from a single point on the globe, could send shockwaves through the entire human system, revealing the deep interconnectedness and shared vulnerability of all nations. The immediate shock was devastating, but the true test was endurance. Could humanity's empires and cultures withstand a generation of twilight and scarcity, as a true super-eruption might cause? Or would the long winter claim them, leaving only ruins and whispers for future archaeologists to uncover? We have mapped the ancient scars on our planet's surface. We know the giants are not gone, merely sleeping. The question is no longer if another will awaken, but when, and are we ready? Today, we possess knowledge our ancestors could only dream of. Beneath the serene beauty of Yellowstone National Park, a colossal magma chamber churns, a system we monitor with an array of sophisticated instruments. Satellites track ground deformation with millimeter precision, seismometers listen for the faintest tremors of moving magma, and sensors analyze the chemical composition of gases venting from the Earth. Similar vigils are kept at other known supervolcanoes, from Campi Flegrei in Italy to Lake Taupō in New Zealand. This ability to see the threat developing is our greatest advantage. An impending super-eruption would likely announce itself months, if not years, in advance through a crescendo of geological activity. This warning would be our window to act. But our modern world also possesses unique vulnerabilities. Our globalized civilization runs on intricate, just-in-time supply chains. The grounding of global air travel due to volcanic ash, the collapse of satellite communications, and the disruption of international trade would be immediate and catastrophic. A multi-year volcanic winter would cripple modern, high-yield agriculture, which is optimized for stable, predictable climates. The very systems that sustain our 8 billion people could be the first casualties. So, what can be done? Scientists are exploring audacious, long-term ideas, such as drilling into the sides of a magma chamber to circulate water and cool it down, slowly releasing its energy over centuries. While this remains in the realm of science fiction for now, more practical preparations are within our grasp. Developing resilient food systems is paramount. This includes creating vast strategic grain reserves, similar to strategic petroleum reserves, and investing heavily in alternative food production methods like hydroponics and vertical farming, which can operate in controlled environments independent of sunlight and weather. We would also need robust plans for relocating populations from affected zones and managing the immense social and economic fallout. The challenge is one of scale and political will. Preparing for a low-probability, high-impact event is difficult in a world focused on more immediate crises. Our technology gives us the power to see the threat coming. But knowledge alone is not a shield. The ultimate test will be one of collective global action and foresight in the face of a true planetary challenge. The ground beneath our feet feels solid, permanent. But this is an illusion. We are inhabitants of a dynamic, ever-changing world, shaped by forces of unimaginable power. For too long, we have viewed supervolcanoes as monstrous aberrations, as villains in our planet's story. But this perspective misses a deeper truth. Volcanism is not an enemy of life, it is one of its essential architects. The very air we breathe, rich in nitrogen and carbon dioxide, was first outgassed from the planet's interior by volcanoes. The water in our oceans was delivered, in part, as steam from countless eruptions. The fertile soils that form the breadbaskets of the world are composed of weathered volcanic ash, rich in essential minerals. These immense eruptions, destructive as they are part of the planet's vital, self-regulating cycle. They are the Earth breathing. The story of life on this planet is inextricably linked to this geological pulse. Mass extinctions, some potentially linked to massive flood basalt eruptions, have cleared the slate, allowing for new forms of life to emerge and diversify. The aftermath of a super-eruption, while devastating in the short term, eventually enriches the land, creating new habitats and opportunities. Life has always endured. It has adapted, evolved, and returned, often stronger and more varied than before. Our own species, Homo sapiens, was shaped by this volatility. We survived the Taupō super-eruption 74,000 years ago, a potential evolutionary bottleneck that may have forged us into the adaptable, resilient, and cooperative beings we are today. Our intelligence is a survival tool honed by a world of unpredictable change. To live on a restless planet is to accept that we are not its masters. We are a part of a system far older, larger, and more powerful than our civilizations. Our challenge is not to conquer these forces, but to learn to live with them. This requires a shift in perspective, from fear to respect, from ignorance to understanding. By studying these ancient events, we learn about our vulnerabilities, but we also learn about our own remarkable capacity for endurance. The future of humanity may depend on our ability to internalize this lesson. We cannot tame the planet's inner fire. We cannot command the continents to be still. But we can learn, we can prepare, and we can listen to the deep, slow rhythm of the Earth. Our future depends not on dominating the planet, but on understanding our place within its epic, ongoing story.